Today we'll be talking about regularization, sparsity, and Lasso. So just to recap, should be a very familiar figure at this point, but we're still talking about supervised learning. We have a training data that's supervised. We choose a model class or a collection of model classes, which will be the thing we'll be focusing on this lecture. What does that mean, a collection of model classes? We choose a loss function. We do some sort of model selection, perhaps via using a validation set. In this example, we're doing cross-validation, where we're permuting what is the validation set around different splits. We train this objective function on each of the training validation splits, and we train it using stochastic gradient descent or a variant of it. And then we select the best model, and then we deploy that model. So this is sort of the complete pipeline that we have seen up to this point. Okay, so in this lecture, we'll be focusing on the concept of what does it mean to have different model classes. And once that is clear, it becomes more clear what it means to do things like cross-validation and model selection. Model selection simply means selecting amongst different model classes. Okay, so option one. Now we've seen a number of different learning approaches. There are, like largely based on linear models, but a few nonlinear examples. So we could say, okay, well, one approach is to optimize an SVM, another approach, and then optimize a deep neural net, or logistic regression, or least squares regression, and we just see which one does better on the validation side. That's one way of doing model selection. The second option, which is the focus of this lecture, is, okay, we're going to do model selection through the perspective of regularization. So first, a little bit of notation. So when we do regularization in this class, the bulk of it will be revolving on the concept of norms. These days, in modern machine learning, there's a number of other forms of regularization that people do, but for this lecture, let's just keep it at the classical notions. So the first norm is an L0 norm. It's not actually a norm, by the way, in terms of the mathematical definition of a norm. And an L0 norm simply counts the number of non-zero entries in your weight vector. In the case where you have a parameter vector W, so I'm ignoring the bias term for now. You have a parameter vector W. The L0 norm of W simply just counts the number of non-zero entries of W. So this is an indicator function. It's 0 if the indicator clause is not satisfied, and it's 1 if the indicator clause is satisfied. Yeah, so it's 1 if each entry is non-zero, so you sum that up. The next norm we're talking about is the L1 norm. The L1 norm is the sum of absolute values. So you just loop through all the entries of your weight vector, and you take the sum of the absolute values of those entries. The next norm is the L2 norm, or more often it's used, the squared L2 norm is used. The L2 norm is, in some sense, the canonical norm, or the most standard norm. It is the square root of the sum of squares of the entries, also known as the square root of W transpose W, same thing. In machine learning, we typically use the square of the L2 norm. So you saw that in the previous lecture with support vector machines, and we'll talk about that this term in more mathematical detail in this lecture. So we typically use the square of the L2 norm, so the squared L2 norm, which is just W transpose W. And the last one that sometimes is used is the L infinity norm, and that is the max absolute value. So the notation is typically written as right here, the max L2, the L infinity norm. And if you think of this as a family of norms, so you take the sum of the absolute values raised to a power of p, and then you take the pth root of that. Then p equals 1 is the L1 norm, p equals 2 is the squared norm, L2 norm. And the L infinity norm is simply the limit as p goes to infinity. And as you think the limit as this goes to infinity, it simply boils down to the maximum, single maximum absolute value amongst all the entries. So these are the family of norms that are relevant to machine learning. The first one is not really a norm, but I added it there to provide some context and intuition that will become relevant later in this lecture. Okay, so another sort of simplifying assumption in terms of the notation is that when we talk about the term regression, I typically mean minimizing L2 squared error. So least squares regression. When we're minimizing some other loss function, we typically use an extra adjective. So for example, logistic regression is minimizing log loss. But if I just say regression, it means minimizing squared loss by default. And the reason I say this is because, first, regression is one of the most popular things we do in machine learning. And second of all, everything in this lecture will be based on regression. And we'll be looking at the regularization term. So everything, we're just going to use regression, the squared loss, keep this constant, and reason about this guy. Of course, in practice, you can play around with both. OK, so this learning objective is called ridge regression. It's simply L2 regularized least squares regression. And the way we're going to think about this, these two terms in this lecture, is we have one that is training loss. So this is one we've been looking at for the last 3 lectures. And it simply characterizes the mismatch between our model's prediction and the target prediction in the supervised training set that we've collected. And so this is something we're quite familiar with. We want to minimize the training loss. This other term that I've introduced is called regularization. And it's a way of characterizing complexity of the model class that we're optimizing over. So the smaller this regularization term is, the quote unquote simpler the model class is. And I'll make this a little bit more concrete in a few slides. And so what we're doing here in this training objective is we're minimizing a compromise or a trade-off between model complexity and training loss. And the lambda here is a hyperparameter that you set that controls this trade-off. So how much do you care about one versus the other? And as we will see, each choice of lambda gives us a new model class. So in a sense, when we do cross-validation, one of the things we're doing is setting the lambda. OK, so let's go through just a simple example. So x has 2 features in this very simple example. The first feature is an age threshold. The second feature is gender. And the target is a height threshold. So this is a very, very simple toy example. And we can train a regression model with some regularization. And let's suppose that's the training set, and that's the test set. OK? So as we increase lambda, so this is the solution of W and B, as lambda increases. So what is the solution to this minimization problem as lambda increases? So when lambda is 0, this is the solution. And as lambda gets larger to something that's very, very large, I forget what I used for this. Maybe it was like 10,000 or something. This is the solution. And we could also plot the training and test loss of these different W's. 1,000, excuse me. Or to say, no, excuse me, this is 10 to the minus 2 to 10 to about 1. Oh, yeah, it's a small training set, of course. And so this is the training and test loss as we increase lambda. So when lambda is 0, so or very small, close to 0, we are not regularizing at all, which means we want to minimize the training error as much as possible. So the training error is quite low, right? Here's the training loss. Here's the squared error on the training loss. It's pretty low. And here's the test error, the squared loss on the test set. And it's much higher, so we're overfitting. Okay? Yes.
In the test error, are you excluding the regularization?
This is in both of these in this figure, I'm excluding the regularization term in both. Yeah. So this is simply I'm training W and B on the training set according to this objective function, but this figure, this is a good question. This figure is plotted using only the right-hand side, summed over either the training set or the test set. Because ultimately, we care about only the right-hand side summed on the test set, which we don't have access to. That's ultimately what we care about. And so here I'm plotting the training error, so only the squared loss part of the learning objective, and the test error, only the squared loss part. So we can see a few things. First, as lambda increases, our squared error on the training set, the training loss goes up. And in fact, if you notice, in the limit of lambda being very, very large, the W actually goes to 0, and the B, the bias term, becomes actually the average, right? What is the average Y in our training set? 2/3, because it's negated, or let's see, it's either, well, okay, I always get confused if it's plus B or minus B, but it's it's 2/3. The test set, what's interesting here is look at the test set error, right? As we increase regularization, we're overfitting all, in this simple example, we're overfitting the entire time by a lot. But you notice that we overfit less, as lambda increases. And the test error is lowest for this intermediate value of lambda. So as lambda increases, our model becomes simpler and simpler. And so the training error even goes up, because we're not fitting the training set very well. And if you look at the gap between the blue line and the red line, the gap should be going lower as lambda increases. But there's this sweet spot in the middle where the training error hasn't started to go up that much, and the test error is going, and the gap is going down faster than the training error is going up, and that's the sweet spot that maximizes the test performance. We had another version of this intuition in the linear quadratic cubic regression example in lecture 1. Was that lecture? Yeah, I think it was lecture 1, where even though the cubic function, which has the biggest model capacity, the most complicated model class, could fit the training data really, really well, we wanted to use the quadratic because we didn't have enough data and we wanted to overfit less. And that's the same intuition happening here. But simply here, we're just varying the choice of lambda in the learning objective rather than choosing a completely different function class. Yes?
Would this still work if you included the bias and your weight effectively?
If I regularized B?
Yeah.
Yes, it would still work. People typically don't regularize B, but yes. It will look, the qualitative difference you see, the qualitative patterns you see on the top figure will stay the same. Obviously, some of the details will be different. Yeah. OK. So here's the updated pipeline that we'll be working with today. The only thing that's changed is the fact that I added this lambda to the learning objective. If lambda equals 0, I get the original learning objective that we've been looking at in lectures up until now. And model selection and validation is simply to be used for choosing lambda. If we hold out some of the training set for validation, we could use that as a proxy for test set performance, and we can see which choice of lambda gives us the best validation set performance. OK, so here I am showing you the score, the raw score of F, right? Remember that the third column, or the fourth, if you will, is the target Y. And we're trying to predict Y as accurately as possible in terms of squared loss, given a linear combination of the first two features in columns 2 and 3. And what I'm showing you here is the prediction on these examples of a solution of a WMB with increasing lambda. And there's a few things to notice. First of all, with lambda really small, which is this column right here, our model is trying to do as well as possible on the training examples. It doesn't, we don't see the test examples. This is just sort of a thought experiment. We don't actually know what these are in practice, but here's what they are. And as lambda increases, we basically predict the average. On average, 2/3 of the people have height above 55 inches, at least in the training set. So W goes to 0, we're just going to predict a single average. And it's easy to sort of derive that if W is forced to be 0, the B, the bias term that minimizes squared loss, is the average. That's an easy exercise. Okay. And of course, as you might expect, the optimal choice of lambda depends on the size of your training data. So here is an example with 25. So I should just mention that these details aren't super important, but this is a 25-dimensional space, randomly generated linear response function plus noise. So here we have 25 training points. I'm plotting test loss, by the way. Here's 50, 75, and 100. So at 25 training examples, if lambda is too small, at least within the range that I'm plotting here, between 10 to the -2 to 10 to the +2, then we're overfitting really, really badly to the training set. And the best test set performance is over here. At 50 examples, the best test set performance is still over here, but because we have more training data, we're not overfitting so badly, even with small lambda. And by the time we get to 100 training points, I think the best lambda is over here. And of course, if you set lambda even smaller, it'll start to go up a little bit. Yes?
How many values of lambda would you test?
I forget exactly. Probably like 5 or 6.
Okay, so
Yeah.
it's not actually like.
Oh, it's not a continuous curve, a line, you mean?
Right, it just seems like pretty sharp.
Yeah, so yeah, you could certainly try more values of lambda if you want.
I was just wondering if you could just go like that.
Yeah, I guess if I try more values of lambda, you'll get something that's a little bit of a smoother curve. I mean, of course, I just connected all the points. Right? It's a plot, right? But if you try more values of lambda, it'll have a smoother behavior around here. Yeah. One of the reasons why I didn't, and perhaps I should the next time to make it more clear, is because in practice, of course, we have much more than 25 training examples. We get curves that look, doesn't look like this. Right? You get it like a nice. In practice, what happens most of the time, if you ever try this in practice, is you get a nice little region where lambda, the behavior of the model with respect to lambda is pretty stable, like how badly it's overfitting is pretty stable, and then as lambda becomes too small, too large, the test performance goes up. And so in practice, you should expect that there's a stable region of lambda values. And the stable region, perhaps here, I have to really sample these values of lambda for this example with 25 training samples. But in practice, you should expect things to look more like this at the bottom right. Okay, so that was ridge regression, or L2 regularized least squares regression. This is the learning objective. Large lambda leads us to have more stable predictions. When lambda equals infinity, the W vector becomes 0. And so all we're learning is the bias, which is the average of the y's on the training set. So if lambda is too large, we're going to underfit the data. And of course, this works with other loss functions too. If you replace squared loss with the hinge loss, you get back support vector machines. Any questions on that so far? Okay, so as an aside, we're going to solve these things using some variant of gradient descent, or more common these days, stochastic gradient descent. And recall that in stochastic gradient descent, we started with this intuition that we can decompose this overall loss function into a number of additive terms. And let's say we do it this way. This is one way to do it. It's one of my favorite ways. It's not the only way. And what this does is it says, okay, I'm going to chop up this guy into capital N small pieces, or capital N is the number of training examples. And now this is my little piece of loss function, like that. And now I can do SGD on this. And of course, if I'm doing mini batch SGD, where a batch is more than just one training example, I could reweight this proportionally. And of course, some people, you could also have n plus 1 pieces of loss functions that you decompose additively, n over here and 1 right here. You can do that too. But but as long as you sort of understand this idea of decomposing the loss function additively, you could decompose it however you'd like, and then you apply SGD accordingly. Any questions on that? Okay. Now let's get into some of the more sort of mathematical interpretations of what's going on. Okay, what I described to you was a largely empirical exercise, right? I gave you this learning objective augmented with this regularization term controlled by a hyperparameter lambda. I give you some empirical examples of how it can control for overfitting. I showed how it can fit into the validation/cross-validation pipeline to select the lambda that has your model class overfit the least. So that all seems to work out. And in fact, if you use standard machine learning toolkits, it'll ask you to set the hyperparameter on the regularization strength. However, this is not a model class, at least the way we're interpreting it right now. It's an optimization problem. So is there a connection between the model class and the optimization? Anyone have any ideas? I mean, I'll tell you in the next slide, but. Okay, so let's move on. So norm constrained model classes. That's the model class, set of model classes we're going to look at. Okay, so we're going to look at the set of, in this case, linear models. And this works for nonlinear models too, like neural nets. And we're going to look at the set of linear models, but we're only going to look at the set of linear models that live inside, in this case, an L2 ball of radius C. So for two-dimensional models, C equals 1 is all the, we only consider W that live inside this red circle. For C equals 2, we only consider W that live inside this green circle. For C equals 3, we only consider W that live inside this blue circle. Right. And OK, so here I'm plotting the L2 norm of the W. That's the result of this optimization problem. So the L2 norm. And as lambda increases, the W gets smaller. Right? And as C decreases, the W that you'll learn will also get smaller. And furthermore, we can sort of here we have it's clear to see that we have different model classes here, right? The C equals 1 is the model class of all W that live inside this red circle. That's a different model class than the set of models that live inside the green circle. And in fact, it is a strict subset of the class of models that live inside the green circle. So by implication, the model class for C equals 1 is strictly less expressive or less complex than the model class of C equals 2, because anything you could learn in C equals 1, you could learn in C equals 2, because one is a strict subset of the other. Okay. So there seems to be a correspondence between this objective function that we're optimizing and this more straightforward model class interpretation that is consistent with the notion of model classes that we've been talking about in class so far. Now does anyone see a connection? Oh, someone must be brave. Yes?
I mean, we're basically like discouraging models, but not strictly saying they can't happen.
True. There's a more mathematically precise connection that I'm looking for. You learn it in multivariable calculus. Or I guess you guys may have learned it in high school. So the connection is in Lagrange multipliers. So here is my learning objective. So just for simplicity, we're going to omit the bias term B, and we're only going to have one training data for simplicity. So this is just one training example. This of course generalizes to more than that. And so here's the squared loss of that one training example. Okay, and so if we're here, if our W is this point, we want to go in this direction. That's the negative direction of the gradient. This is the minimizer right here. So the darker. So this is the. Sorry, excuse me. I should explain. This color coding corresponds to this loss function. So the minimizer is right here. So if our W is right here, the negative gradient goes in this direction. If our W is right here, the negative gradient goes in this direction. So on. Okay. Now let's say, okay, we don't want to learn over all possible W. I don't want to learn over all possible W. I only want to learn the loss minimizer for W whose radius is less, or squared radius, I guess, or whose squared radius is less than C, or whose radius is less than square root of C. So let's start with a W that lives inside our model class. So this is a W that lives inside our model class. This is the direction of the negative gradient that we would do to do gradient descent. If we are on the boundary of the model class, so here we're on the boundary of the model class. We're not allowed to go outside the boundary, and yet the gradient would take us, a gradient step would take us outside of the boundary. What you would do in this case is you could say, okay, I'm going to project this gradient update back onto the boundary. So this is the actual update I would do. And then if I'm at this point, this is the gradient. Well, actually, this gradient, and I did this, this gradient is actually parallel to the tangent vector of the boundary of this function class. Right. So this is the tangent of the circle, and these two things are exactly parallel. What does that mean? If I project the gradient update back onto the boundary of my function class, I get the exact same point back. So the optimality condition, and this is, by the way, this is basically the intuition behind Lagrange multipliers. And so the optimality condition is that we have this constraint boundary. We have some sort of constraint. In this case, it's the boundary of the model class. And we're not allowed to learn a model that lies outside this boundary. The optimality condition is that the gradient are aligned. The tangent of the constraint boundary and the gradient on the loss function, those two are exactly parallel. And that is a sufficient condition for optimality. A couple other conditions, but that is one of the sufficient conditions you need for optimality. In other words, there exists a lambda, right? So let lambda be the scaling factor, okay? So this is the tangent to the surface. This is the gradient to the gradient of the loss function. When they're parallel, that means one is a scalar multiple of the other. That's what it means for the two to be parallel. And that means that there exists a lambda such that one is lambda times the other. So there exists a lambda such that the gradient of the loss function, and again, we're doing gradient descent, so we have to negate it, is equal to minus lambda times the tangent normal, the tangent of the constraint boundary over a model class. The other condition is that, and this is the one that's required from the beginning, is that our model class, the model that we're learning is within the boundary, Yeah. Okay, so we have this norm-constrained model class training that we've just looked at. This is what it is. This looks a lot like the kind of learning problems that we're familiar with, right? We choose a function class or a model class, and within that model class, we want the minimum training loss model. So what does that mean here? We want a model W that minimizes this training loss, but our model class is the set of all linear models whose squared L2 norm is less than C. That's our model class. So this looks very much like the type of model class selection type definition of learning that we've seen. Here's our observation about optimality that we just saw in the previous slide. These are the two conditions that must be satisfied at optimality. Okay, so we can write out what's called the Lagrangian. And the Lagrangian is simply the original loss function plus this constraint times what's called a Lagrange multiplier, which is the lambda. And the claim is that solving the Lagrangian will solve the original norm-constrained training problem. So solving this guy will solve this guy. So okay, let's just do a little bit of calculus. So let's take the gradient of the Lagrangian with respect to W. And so what that gets us is, we apply the gradient. We apply the gradient on this guy and apply chain rule, so we get this. Sorry, on this guy. Excuse me, on this guy. And so we get this. And at the optimality, of course, the gradient equals 0 at the optimality. So we set this equal to 0. We move this guy over here, and we get this equality at optimality. So if we look at if we take the gradient with respect to W of this Lagrangian, and then we set it to 0, and then here's an equality that must be satisfied at the optimal solution to this Lagrangian. This is exactly the optimality that we saw up there, where the gradient of the loss function must be a scalar multiplo of the gradient of the tangent to the function boundary. So indeed, if the optimal solution to this guy satisfies the first optimality condition for the top learning objective. So this satisfies the first condition. Okay, now let's take the gradient with respect to lambda. So here's our Lagrangian. We're now going to take the gradient with respect to lambda, which is a free parameter that we've introduced to this in the Lagrangian version of the optimization problem. So let's take the gradient with respect to lambda. And I should say that lambda is strictly greater than 0. Or excuse me, the lambda is constrained to be non-negative. I should have written that here. And what you get is that if this guy is negative, then lambda must be 0. Okay, and if lambda is 0, the gradient is 0. If this guy is at or beyond the boundary of our constraints, then the gradient is simply, if you take the derivative of this with respect to lambda, you just get this term back. Setting this to equal to 0, because at optimality the gradient of lambda must equal 0, then the first if clause is vacuous, which is trivially satisfied. The second if clause implies this. Because the only way that this can be 0 is if we push W transpose W to a point where it is less than or equal to C. Otherwise, this is strictly positive. And so that satisfies the second optimality, second condition for optimality for this objective. Okay. Any questions on this? Yes?
Could you explain again why the gradient with respect to lambda was 0 when the norm was less than c?
Yeah, so it's a little bit hard to see from the equation, but if lambda is constrained to be non-negative, so lambda is constrained to be non-negative, then let's see, what's the best way to explain this? I'm trying to think of the best way to explain this. So if lambda is constrained to be non-negative, then what happens is that if W transpose W C is greater than is negative, then lambda has to increase because we're gradient descent. I may have skipped a step. I apologize in this slide. Okay. So this guy, if W transpose W is less than C, then this is negative. And since we're minimizing this, we want lambda to be large, to get bigger. And that implies I'm having one of those moments where there's something in my brain, I know it's right there in the back of my brain, and you guys are all staring at me. And the more I realize you guys are all staring at me, the harder it is to retrieve that piece of information in the back of my brain. Yeah. Maybe I'll explain the Piazza post after class. Yeah. Yeah, I apologize. I'm just having one of those moments right now where the more I think, the harder it seems to remember. But I will follow up on a Piazza post after class. Sorry about that. Yes?
Your expression of optimality, like the observation of optimality box, so you're trying to say that the direction of the loss should line up with the direction of the normal vector of the constraint set.
Right here,
right?
Yeah.
Okay, so I see the gradient of loss. What is the thing it's equal to? I don't understand.
This guy?
Yeah.
So, right. So this is equivalent to by vector algebra, vector calculus. This is equal to 2 times W. So 2 times W. So the gradient of W transpose W, the gradient with respect to W of W transpose W is equal to 2 times W. It's just a vector calculus identity. Just like the derivative of x, the derivative with respect to f of x squared is 2x. Yeah. By the way, there's a recitation tonight on linear algebra and vector calculus. And so, that's why when you take the gradient with respect to W of this thing, this guy, you get 2x y minus W transpose x, which is just the gradient of this guy. So 2 is from the gradient of the derivative of this guy. Then you apply chain rule inside the middle. Sorry, if you apply the gradient of W with respect to this guy, you take the derivative of this term, which is just 2 times this term. Then you apply chain rule on this little thing inside, which is just x. And if you apply the gradient with respect to W of this term, well, first of all, W doesn't appear here. This part disappears. It's just 2W times lambda. And then I'm going to shift things around. So I move this over here and negate the whole thing, and I get this equality. And this is just a vector calculus way of deriving this. The intuition, of course, follows the geometric interpretation. Looks like this. Okay. So the whole reason for going through all of that is to draw a connection between these two. So this was the learning objective that we looked at in the first 15, 20 minutes of class today, and observed that it seems to provide a way of controlling for overfitting. And it's certainly in the limit as lambda goes to infinity, in the limit as lambda goes to infinity, then the solution to this optimization problem must have w equals 0, because otherwise we pay an infinite cost on this guy. And so again, I'm omitting the b here, but then we just learn the bias as the average. So certainly in the limit as lambda goes to infinity, we can see that this learns a simpler function. But in between values of lambda, we observed empirically that it seems to learn simpler functions. And what the purpose of this entire exercise is to draw a tight mathematical connection between that intuition and our normal notion of function classes that we've covered in class up to this point, where a function class is function class A is more complex than function class B if function class A is a superset of function class B. Right? All linear functions are quadratic functions. Therefore, quadratic functions are more complex than linear functions. All quadratic functions are cubic functions. Therefore, the cubic function class is bigger than the quadratic function class. In this case, all linear models with living in a smaller ball are also linear models living inside a bigger ball. Therefore, if C is bigger, it's a strict superclass of a smaller C. Therefore, it's more complex. That's the standard definition of model complexity. That's one of the standard definitions of model complexity. And the purpose of this entire exercise is to draw a mathematical connection between this thing that we do the majority of the time in machine learning and this interpretation, which, of course, we don't do directly in machine learning typically these days, but it is the more mathematically clear interpretation. And they're connected via Lagrange multipliers. So the Lagrangian corresponds to norm constrained training. And if you hold a lambda fixed, so if I just decide to hold a lambda fixed, then it reduces to this guy, because if I hold lambda fixed, the C is irrelevant. And so you can show that for any choice of C, well, subject to some degenerate cases, but for any choice of C, there exists some lambda that solves this problem that gives you the equivalent solution. So when you try different values of lambda, when you're doing model selection via cross-validation, let's say, you're implicitly trying different values of C. And that's the mathematical connection. Even though this objective on the top right is what we do in practice, because from an optimization standpoint, it's much more convenient. From an interpretation of what's going on in terms of model complexity, this is the Lagrangians what connects these two together. And so now we can think about it in terms of model complexity, in terms of the size of function classes. And we don't need to make this connection explicit. We just need to understand that for every choice of lambda that we're trying when we're doing validation and tuning lambda on a validation set, it's equivalent to trying some C in this optimization problem. But we're just not explicitly doing it because it's less convenient from an optimization standpoint. Yes.
Do people ever simultaneously fit the weights and and lambda
on a training set?
Yeah, I guess.
Typically, no, because you're double dipping your training set. you typically use a validation set. Yes?
I guess, so with the validation set, is it possible to get some sort of like gradient on loss with respect to lambda? Like, can you know which direction you should either increase or decrease lambda based on?
I'm not sure I understand the question.
So with your validation set, you get some like error, right? And then you have your parameters like, and so like, can you do like gradient descent for like lambda?
Oh, no. Because your lambda, you could do gradient descent. So you could as Lagrangian, and so you fix a C and you solve for the optimal W and lambda. You could do that, but then you have to set your C on the validation set, right? And so you might as well just not solve the Lagrangian, and just solve this guy and just set your lambda on the validation set. So the most like, I don't know if I should use this word in class, but like the most anal way of doing this, mathematically anal way of doing this, is if we start with this as our interpretation, because this is like the one that's cleanest in terms of the conceptual interpretation, then the way we control for overfitting is we set the C on the validation set. And so then we would solve the Lagrangian by solving for both W and lambda on the training set for a fixed C, and then varying C on a validation set. But in practice, why would we do that? Because if for any C, there's some lambda that gives us the optimal solution, why don't we just solve this problem, which is a lot easier to solve computationally, and just try different values of lambda? Does that make sense? Or yeah, so you do get a gradient on lambda in the Lagrangian on the training set, but then you have to try different values of C on the validation set. So there's no point in practice. This is probably the most important slide in the lecture today. So just want to make sure we take a little bit of time to absorb it. Yes?
So let's say like we were doing classification and we only cared about like the sign of the score.
Right.
And so isn't it for any like value of C, like the bound of the norm, we could still the whole range of linear models is still like contained in that. You could just scale it up. Just scale any model down to fit into that norm range.
That's true if it's linearly separable. It's not true if it's not linearly separable in high dimensions. Because if you scale, because then you will scale some scores up and then other scores down. If it's not linearly separable, that's not true in high dimensions. It's hard to get at that intuition with two-dimensional visualizations, but if you have 1,000 features, that's just not true. Okay. Just to recap, L2 regularized least squares is equivalent to solving a norm-constrained model where we're doing least squares regression on a model class where the norm of W cannot be too large. That's our model class. Larger lambda leads to more stable predictions, less likely to overfit the training data. If lambda is too large, you underfit. Correspondingly, if smaller C corresponds to more stable predictions, for example, if C equals 0, then W has to equal 0. And the only thing we can learn is the bias term. C equals 0 equals lambda equals infinity, for example. And so if C is too small, we underfit as well, correspondingly. And of course, this works with other loss functions as well, not just squared loss, log loss, hinge loss, etc. OK, so as an aside, there's another way that we can think about regularization, and that is by hallucinating data points. So in this example, it's cleanest with ridge regression, so I'll just do it with ridge regression. So here's the ridge regression learning objective, and this is the gradient with respect to the ridge regression learning objective. So suppose we did not do this regularization term, and we just added some fictitious data points. And this is a d-dimensional space. We're going to add d data points, and they look like this. So each data point is a scaled basis vector. So e sub d is a basis vector that is 0 in all the entries except for 1 in the dth dimension. And we're going to scale it up by square root of lambda. And the target, the supervised target, is 0. Okay, so we're going to add capital D of these hallucinated training examples. So this is our new learning objective. So instead of regularization, we're just going to hallucinate these data points and add it to the training set. And this is the squared loss of those training examples. Okay. So let's take the gradient with respect to this learning objective with the hallucinated data points. So the right term is the same as before, and the left term is simply taking the gradient with respect to with respect to the hallucinated data points. And if you simplify, you get back this, which is exactly the gradient you get for L2 regularization. So it turns out that, at least in the case of ridge regression, imposing this L2 regularization is also equivalent to saying, well, in the absence of data, real data, I'm just going to pretend that I have these data points. And so what these data points say is that I want to be 0 along any of the directions, and I need a lot of training data to overwhelm my hallucinated data points. And by the way, hallucinating data points is actually a thing that people do in practice. Maybe not for linear regression, but certainly in many applications, people hallucinate data points to stabilize training. These days, they call it a different term. They call it data augmentation. But it has the same roots and same motivations. OK, so another small thing, multitask learning. So suppose we have 2 prediction tasks. We want to learn 2 spam filters. And in particular, these spam filters are going to be personalized to the individual preferences of 2 people, Alice and Bob. And we have limited training data for both. So we don't have that much data for Alice. We don't have that much data for Bob. But we can make an assumption, it's perhaps a reasonable assumption, that Alice is similar to Bob. So what does that mean? That means we have 2 training sets where the number of training examples are relatively small, not that large. So option 1 is, OK, let's just train 2 different models. I'll just denote them by W and V separately for the two tasks, and separately, completely separately. OK, well, because the training sets are small, both models will have high error on the test set. Another way we can do this is train them jointly. OK, we're going to have a single optimization problem that has both the loss on the first task and the loss on the second task. Actually, this doesn't actually do anything, because these 2 objectives are completely decoupled from each other. Solving this joint objective is equivalent to solving them separately. So just adding the 2 together doesn't do anything. There's no interaction between the 2 tasks. OK, so this brings us to multitask regularization. In multitask regularization, we have the standard regularization terms we have the training loss and the two objectives, and we have this multitask regularizer. There's multiple ways of doing this. I'm giving you here the simplest way, which is simply saying I want to also minimize the distance between W and V. That's what this is, right? This is W minus V transpose W minus V is simply the square distance between W and V. And so I want to learn a W and V that has low training error on their respective training sets, are not too complicated as measured by standard regularization, and are not too far from each other. So all other things being equal, we prefer W and V to be close to each other, and how much we prefer that is controlled by another hyperparameter, which I call gamma. And so here I'm holding lambda fixed, and I am just plotting the test loss on, in this case, task 2 for different values of gamma. And this is a synthetic data set, but I think the curve qualitatively illustrates my point, which is that in the beginning, when gamma is really low, we get pretty high test loss on task 2. Because task 2 and task 1 have some similarities, as I increase gamma, I can share statistical strength, right? Because I have training data for task 1, and I know that the model I learned for task 1 is similar. So as I increase gamma and I force these two to be similar, the test loss actually decreases. But then if I hit gamma too high, in particular if gamma is infinity, then I force W and V to be exactly equal, then test loss goes back up. Yes?
So how does this compare to if we combine the data and just use one?
Excellent question. So how does this compare to if we just combine the data and then have an extra feature that's like, is this task 1 or task 2? So I have a couple comments on this. So first of all, if you're going to do linear models, that might not work very well. Because then you're basically saying that the difference between task 1 and task 2 is an additive offset, because it's a linear model. If you have a nonlinear model, then maybe you could do something there. But you're not relying on your function class to be able to learn some complicated relationship between that new feature you introduced and the other features. Whereas this relationship is much more explicit. So it depends. The answer is it depends. But certainly in the linear case, this gives you a much more explicit assumption on the relationship. And in the linear case, if you just add an extra idea like that, it's probably not going to work very well, unless you're pretty confident that the only relationship between the two is an additive offset, because that's what that weight vector is going to learn. That new weight feature weighting is going to learn. Okay. Any questions? Okay, I'm going to close off the lecture with Lasso. So Lasso also is another word for L1 regularized least squares regression. So L1 is different from L2. In L1, we take the sum of the absolute, we regularize by measuring the sum of the absolute values of the entries of W rather than the sum of squares. So this is L1, right? This is Lasso, and this is Ridge. And so we can think about some comparisons between L1 and L2. So in L2, if we think about this objective function, the penalty that we pay between having W be square root of 2 versus the W being 1 is equal to the penalty we pay between W equal 1 and W equal 0. Right? That the increase in this objective function, at least in terms of the regularization part, from 1 to square root of 2, is equal to the increase in penalty from 0 to 1. Whereas in L1, excuse me, the increase in penalty between 0 to 1 is equal to the increase in penalty between 1 and 2. And you could see that in the shape of the regularization penalty curves in this figure, where L1 is in red and L2 squared L2 is in blue. Okay, so just as an aside on the subgradient, the subgradient of a convex function is a set of all possible tangent slope lines that lie beneath the function. that's sort of the informal way of saying it. Here's the formal definition. The subgradient of a convex function is the set of all possible tangent slope lines that lie beneath the function. That's sort of the informal way of saying it. Here's the formal definition. The subgradient of a convex function is a set of all possible tangent slope lines that lie beneath the function. That's sort of the informal way of saying it. Here's the formal definition. And so if a function is actually is differentiable at a point A, then the subgradient at that point is equal to the gradient. The subgradient is a singleton set, which is just the gradient. However, in L1, we see that the L1 penalty function, the absolute value function, is not differentiable at the origin. And so if W, for any individual dimension of W, if W is negative, then the slope is this. If W is positive, then the slope is this. If the W is in between, is exactly at 0, the slope can be anywhere between -1 and +1. Those are all valid subgradients at W equals 0. And so in practice, actually what we do is stochastic subgradient descent, not stochastic gradient descent. And if you truly are at the origin, you can pick any of these slopes as a valid gradient operator if you want. Okay. So this is the gradient. So we can do gradient descent on this objective. There are better ways of doing this than gradient descent, but it's a little bit beyond the scope of the class. Let's go to the Lagrange multipliers interpretation, because I think this is the most important consequence of using L1 versus L2, or squared L2. So this is sort of the picture we had before when we're unconstraining the model class. For squared L2, the model class boundary is the shape of the model class boundary is a sphere. For L1, the shape of the function class boundary is not a sphere. It is a polyhedron. So, if we are at this point on the boundary, that's the gradient with respect to the loss function, and then we project down to the boundary, and we keep going. And let's say we get to this point, which is on a corner of the boundary, one of the corners of the boundary. There are actually multiple tangents to there are multiple tangents to the boundary here. So at this point, there's only one tangent to the boundary, which is straight, the tangent vector that's normal to the boundary. At this point, there's if we think about it in terms of subgradients, there's an infinite range of tangents to that corner part of the boundary. And so what that means is that there exists, this is, by the way, the optimal solution to the example. What that means is that the gradient of the loss function is contained in the set of subgradients at the boundary, scaled by some scalar multiplier, in this lambda. In the case where the boundary is a differentiable function, there's only this subgradient set is a singleton, the single tangent. In the case where we're at a corner like this, there's a continuous set of tangents. So what this means qualitatively is that when you're regularizing with L1, with the L1 penalty, the solutions you find tend to be at the corners of the boundary of the function class. Yes?
So wait, what's the advantage to training using L1 regularization versus L2? There's three answers I can give you. One is optimization, one is like statistics, and one is related to the point that the solution tends to be at corners. So which are you interested in just all the above, or? Well, like, why would you choose one normally?
Okay, so probably the biggest reason is related to the fact that the solutions tend to be at corners.
So you only have to like check.
Not that you only have to check corners, it's that you want sparse solutions, right? So
if you because of this fact that it's much easier to align the gradient it's much easier for the loss function to match the subgradient and at the corners, because there's an infinite number. Then what that means is that the solutions tend to be at corners, and what that means is that the W you get out of the optimization problem tends to be sparse, many zero entries. That is the biggest reason why people use L1. In other words, a weight vector W is sparse if most of its entries are 0. In other words, it has small L0 norm, right? L0 norm directly measures if the number of non-zero entries. So why not do L0 regularization? Like why do we do L1? Well, the reason, as you might expect, is that L0 is not continuous. It is a flat and discontinuous regularization penalty. Right? It's you're either greater than 0 or you're not, or you're exactly 0. Excuse me, you're either non-zero or you're 0. And either way, the objective function is flat or discontinuous. Just like in 0, 1 loss, it's flat or discontinuous. That's why people don't directly use L0 regularization. And L1 is a continuous function. It's convex, continuous. It's relatively easy to optimize. And we show in the previous picture that it induces sparsity. There's a more formal analysis showing that it induces sparsity, but I think that the intuition suffices for this class. Why might sparsity be important? There are a few different reasons. One is computational and memory efficiency. If you think that a sparse model is accurate, and maybe we don't want to store a huge weight vector. We just want to store a sparse solution. Makes a lot of things more efficient. Sometimes the true model is sparse. Like we really think that the best model that we can learn, the one that really fits the data well, is a sparse W. And so people have studied Lasso for a very, very long time. And so here's just one type of analysis that people have done. If you find this type of analysis interesting, you might be interested in statistical learning theory. But just to state the guarantees of this analysis, suppose the data was generated from a normal distribution, W star transpose X, plus some Gaussian noise with variance sigma squared on the noise. Then, if lambda is sufficiently large, where n here is the number of data points, then with high probability, where the probability increases with the number of data points, the support of the non-zero entries of W is contained in the support of the non-zero entries of W star. What that means is that we have high precision in parameter recovery. We will never say that a feature of W, an element of W is non-zero if it isn't W non-zero in W star. And sometimes high recall. So we can exactly recover, or almost exactly recover, the non-zero entries of W star. Okay, and like I said, this is sort of beyond the scope of the class. I just want to give you a flavor of what statistical learning theory looks like. Okay, so what I'm plotting here is the value of the weight vector for the two of the two features. So for L1 and L2 regularization. So as you increase L1 and L2, the weight vector you learn goes to the origin, and as you decrease it, they increase, of course. And so if you zoom in, you see that at some point, as you increase lambda, the L1 regularization forces the weight on this feature to hit 0 exactly. So the solution is sparse in the sense that only one out of the two elements of the weight vector is non-zero. Yes?
So I have a question about L0. So what would be the situation that we care about sparsity, and also can we employ a similar strategy to hinge loss?
Yeah, you can do L1 regularized hinge loss.
For like, if you want to solve for L0 as well?
Oh, no one solves for L0 in practice. Like,
Okay,
it's a flat and discontinuous function. So it's either flat or discontinuous everywhere. Yeah. It has no gradient. It gives you, like, optimizing it is really hard because it gives you no gradient information. It gives you no useful gradient information.
So what I was trying to ask, like, I don't know if it makes sense, but when we were trying to solve for the 0-1 case, we changed it to solve
hinge loss. Yeah. So that's one of the reasons why we do L1, right?
So it corresponds to the same.
There are similar mathematical reasons for choosing L1. I don't know if the analogy is. There's some analogy. I wouldn't make the analogy too strong because there's some differences. But yes, there's some analogy. I mean, one is symmetric, one's asymmetric, and you know. Yeah. But certainly, there's some analogy. Yeah.
Do you see any relationship between like the number of data points you have and like which regularizer you should use?
No. The number of data points you have corresponds to the strength of the regularizer, the lambda. Which regularizer you want to use really corresponds to what you want to get out of the model. Do you want a sparse model? Yeah. So choosing lambda depends on the size of the training set, but you know the choice of regularization really depends on what you want to get out of the model. Now, of course, you can make the argument that maybe I don't really care, and I'm just going to try everything and do cross validation, see which one has the best validation accuracy. We could always do that, and you kind of throw in a million hyperparameters. But at some point, as a machine learning practitioner, we just can't afford to do that, right? Like that would be a combinatorial explosion of possible things to try, and you will kill yourself on doing that if you do that in the calcul competition in 2.5 weeks or 3 weeks. So these types of insights gives you a handle on is it even worth my time trying? Yes.
Why probably sparse?
Why? Well, okay. So first of all, there's these type of analyses, which I'm not going to prove. If you're interested in proof, it's you can see these references. So if the true W was sparse, and there are many cases where the true W, you can imagine that the true W is sparse, you want to recover it. But even if the true W is not sparse, you simply just want a sparse solution for whatever reason. You want a sparse solution for whatever reason. And there are many reasons in practice. Then here's the intuition about why the L1 penalty induces sparsity. And the reason is that you're going to find a solution that tends to be at corners because you'll hit the boundary of the function class, and then you'll do a gradient update with respect to the loss function, and then you project back onto the boundary, and because it's a linear boundary, you're going to end up at a corner often. And of course, in high dimensions, there's maybe 1,000 or 1,000,000. This is 1,000 or 1,000,000. This isn't like 1,000 or 1,000,000 dimensional space. So there are many partial corners where some of the entries are 0. So every corner corresponds to some subset of the entries being 0. And at the corners, the tangent to the boundary is a continuous set of vectors. So there's more of them. That's the intuition about why the solution tends to be at corners. Okay, so one of the challenges with Lasso is that exactly hitting 0 with gradient descent is really, really hard. You basically need your step size to drop to 0 in order to exactly hit 0. And yet one of the reasons why we want to do lasso is we actually want to recover an exactly sparse vector. And so there are methods of doing this. The most popular one is called iterative soft thresholding. I'm not going to talk about it, but just so you know that these things exist. Okay, so just to recap, Lasso versus Ridge. So Lasso learns a sparse vector. In terms of predicted accuracy, Lasso is often less accurate than Ridge regression. So what people often do is they run Lasso, L1 regularization, to identify which W's are non-zero, and then they throw away the L1 penalty and only look at these dimensions, and then rerun least squares. So it's a two-step learning problem. Yes?
Is there any benefit to doing that over other dimensionality reduction techniques?
So it depends on the nature of the dimensionality reduction. If the dimensionality reduction is feature selection, which is simply saying, I want to learn a linear model in my original feature space, and I just want to choose a set of features, this is one of the better, more popular techniques. There are other forms of dimensional reduction, which we'll cover later in this lecture, or excuse me, later in this class, that do some transformation of the data. And that's a different style of dimensionality reduction. So it depends on what you're looking for. Such as principal component analysis. We'll cover PCA and SVD later in this class. Ease of inspection. So imagine that you want to actually figure out what your model is doing. You want to explain to your boss, oh, I learned this model. I think it's a reasonable model. It's not doing something crazy because I can actually tell you what it's doing. Well, okay, and this you could make the argument that sparse W's are easier to inspect. If there's 1 million dimensions and there's only 15 non-zero entries, that's a lot easier to reason about than if all 1 million were non-zero. And in fact, people these days try to have new notions of sparsity and neural net architectures where certain, well, anyways. So interpretability is a very important challenge. Finally, it actually turns out the lasso is actually in many cases, at least not using naive approaches, harder to optimize than squared L2 norm, but there are some tricks you can do to make it pretty fast. So just a recap of regularization. We have L2, we have L1, Ridge and Lasso, we have multitask, and if you have some sort of prior belief about what you should do if you don't have data, then you could add your own regularization, right? So for example, look at the multitask regularization term, right? Suppose that I have basically 0 data about task 1, then the model I learn is going to be basically dominated by this regularization term and this close to V term, right? So regularization is basically saying, another way of thinking about regularization is basically saying, if I don't have enough data, this is sort of my default answer. And I need data to overwhelm my default answer. Okay, so here's the updated pipeline. We have training data, we have model classes, we have loss functions, and we learn our model class. We learn over different model classes controlled by lambda in terms of regularization, and do validation in this formulation, and then we deploy. That's it. Next week, we'll be looking at decision trees and ensemble methods, and don't forget recitation tonight. Thank you.